Today's lecture will be the properties of Fourier transform. Fourier transform and Fourier series are very similar to each other. However, Fourier transform for periodic, non-periodic, Fourier series for non-periodic, Laplace transform. It is the generic way where Fourier transform is a special case, as we discussed last lecture. When we assume it is convergence, the imaginary axis is B convergence, and also assuming the real part of S equals sigma plus j omega, to assume sigma equals 0, then this used to have a Fourier series, Fourier transform is a special case of Laplace. But this happens under two conditions, or at least two conditions. Today is April 12. Friday, the reading is page 223, 230. Then next week, lectures 415, Monday, page 261 until 263. Then is the due date for homework number 13. Then 417, which is Wednesday, the reading is page 261 until 263. And we should expect to finish Fourier transform by Wednesday. If not, we might do it by Friday. So Friday, also it will be the due date for homework number 14, and also homework number 15. But as we know, homework number 15 is no submission, but it's required for the exam. So here's no submission. So in Friday lecture, it's up to our progress. It might be we'll start the body plots, or if we still have some remainings of Fourier transform, if we haven't finished Fourier transform yet, we will try to finish it by Friday. Okay? Then, as we know, Monday, what's the date? 22nd? It will be exam 3. Okay? So exam 3 will include Fourier series, Fourier transform. And some important tables. These tables are table 5.6 and table 5.7. These tables are associated with Fourier transform. And you can notice the similarity between Fourier transform table, Fourier series table, with slight differences. If you see the differences, basically, you will assume S equal to j omega, and some other functions you might see some additional terms, and these additional terms because even though you assume S equal to j omega, but you will see some situations while the imaginary axis is not convergence, so we need to add some modification. So, not 100%. It's not 100% correct to say Fourier transform equal to j omega when you substitute S equal to j omega alone. But there are some other conditions. If they're mixed, then it will be okay. If not, then there will be some differences. Okay, let's go to the properties of Fourier transform. We already discussed properties of Laplace transform, but we will discuss linear. So linear. Linear means if we assume that Fourier transform of x of t is equal to x of omega. And if we assume the Fourier transform of v of t equals to v of omega, keep in mind when you convert into frequency domain, either Fourier transform or Laplace transform is called frequency domain. Both of them are frequency domain, so they must be uppercase. So x of t from lowercase will be as x uppercase of omega, and v of t will be v uppercase. Keep in mind those will be uppercase. Then, since it's linear, then we can say Fourier transform of ax of t plus v of t. Well, it will be distributed and linear, so it will be ax of omega plus v of omega. So in addition and subtraction, it will be distributed. That's it. So if you do this, it will be fine. Small example as a graphical example. Here is t, here is x of t. Then let's assume these points. Here is 0, 1, negative 1, 2, negative 2. So I'm going to assume it like this way. We're going to assume here's a negative 1, here's a negative 1 and 2. So we need to convert this to Fourier transform. How to do this? You can do it in multiple ways, but there is one way I'm going to use the linear relationship. This is actually equal to this plus this. So here is t, then I will say here is negative, here is 1, here is negative 1, then we've updated 1, and here's 2, here's negative 2, we've updated 1. So basically, if you group add left-hand side, right-hand side together, this yields to x of t. Okay? Does this make sense? So these two. Then how can we model these two, or how can we write the equations, the mathematical equations for this? Here is the width equal to 2 minus negative 2, which is 4. Here the width equal to 1 minus minus 1, which is 2. The other thing here, centered at origin, centered at 0. This one centered at 0 as well. So this is rect function. So we can say the first one is actually rect of t minus center over width. So with this part, it will be, I can say this is part A, this is part B. With part A, it will be rect of t minus 0t over width, which is 4t over 4. While part B, it will be rect t minus 0, which is t over width, which is 2. Okay? We know the rate. We already done this before, which is how to define the rate. Then recall the Fourier transform of a rect of t over tau. We've done this last lecture, which is a tau sinc of omega tau over 2. We already found this last lecture. Now, we will substitute this for A and for B. So we can say x of t equals to A plus B, which is x of t equals to rect of t over 4 plus rect of t over 2. And all the magnitude, amplitude 1 and 1 for each one. Okay. Then, according to the analysis, which is basically we will find Fourier transform of x of t, which is Fourier transform of the first rect and Fourier transform of the second rect. Which is here, the first one will be A. So Fourier transform of the first rect, t over 4, then plus Fourier transform of the second rect, which is t over 2. So here, the first one, which is t over 4, tau equal 4. Here, tau equal 2. So let's do the Fourier transform of the first one, which is A. The amplitude is 1. So it will be 1 times tau, which is 4, times sinc of omega tau over 2, 4 over 2. Then plus 1, which is A, tau, here's 2. Then sinc of omega tau, here 2 over 2. Okay? Then it will be 4 sinc 2 omega plus 2 sine of omega. Okay, does this make sense? Then that's x of omega. I'll give one place. Any question? Let's go to another property. So that one, the first property linear, the second property, which is time scale. Time scaling property. So time scaling says when you have x of a of t, when you do the Fourier transform, it will be 1 over a x of omega over a, such that a here is positive, not negative. Let's assume this example, which is assume we have x of t like this. It's 2, 0, 2. And this is 2. So we can say that the amplitude A equal to the width equal to minus 2, which is 4. Then here tau is actually 2. What else we can conclude, which is centered at 0. So we can say x of t equals to 2 rect of t minus 0, which is t over the width 4 over 4. Okay? That's x of t. To find x of omega, we can use the result that we know about the rect, which will be same. Here it will be 2 times 4 sine of omega t, omega tau, omega times 4 over 2. So it will be as 8 sine of 2 omega. This is x of omega, right? That's what we want. Then let's assume another scenario, which is x of 2t. X of 2t, how this will look like, the waveform. This will change only in the time axis, while the x-axis, it will be the same, or the x of 2t actually will be the same. So here the magnitude is 2, remain the same, but it will shrink the time axis. And we know this when we discuss the first exam material. We know how to shrink this because it's 2t. If the system constant is larger, then it will shrink larger than 1. If the constant is less than 1, it will expand. Right? So it will shrink like this. How can we do this? Do the Fourier series, Fourier transform. We have method number 1 by calculating the width. So the width here, here equal to 2, tau equal to 2, here tau equal to 2. Then what else? Here's it, center elsewhere. So here x of 2t will be 2 rect of t over 2. Then we can say x of 2 omega, something like that. Here, x of omega, this one. It will be as a tau, a which is 2, tau equal to 2, sine of omega, 2 over 2. So as a result, this will be 4 sine of omega. And I would like to write x of 2 omega. I prefer to write which is sometimes I can say x bar of omega, something like that, because I don't want to write it as x of 2 omega to be understood as something different. Then this is method number 1 by using the knowledge that we know from limits. Method, so here, which is here, method number 1, using normal Fourier transform. There is method number 2, using property of Fourier transform. Basically, in part 1, we already calculated x of t at x of t. It will be converted in here to x of omega as 8 sin 2 omega. And we know, using the properties, the Fourier transform of x of 2t will be 1 over 2 x of omega over 2, which is 1 over ax of omega over 2. So, as a result, it will be 1/2 times 8 sin of 2 times omega over 2, then it will be 4 sin of omega. So this is how it should look like. We can compare this one with this one, they are exactly the same. So either ways can be fine. So sometimes there can be multiple ways to do that. Which one do you use? Use the one that's more convenient for you, more easier for you. Okay? So in this lecture now we focused a lot about the sink, even about the rect function. Even when we discussed the last lecture of Fourier series, we discussed a lot about the rect pulse, or the pulse which is rect function. Again, the rect function comes as a pulse. And we know that the rect function, no matter it's series, periodic, or non-periodic, it will be a sink. That's what we discussed. That means we see sink, which is like, we know it will be something like this. Dk equals time. That's the sink function. So now I would like to discuss about the relationship about the time scale of the sink, which is if we increase the time or decrease the time. So here is some Laplace about the sink. So we will assume here tau, which is the width equal 2, equal 1, width equal 1. Then here we'll assume width equal 2, then width equal 4. So we will see how is the first plot, this is time domain, the second plot is frequency or Fourier transform. So it's sink function. So whenever we see the width 1, you will see the sink function look like this way. Then we will make the width equal to 2. So basically we expand the width. So by expanding the width, look at the sink, it will be narrower. Right? So look at width equal 4, to look at the sink. It's pushing. So you can say that when you increase the width, this will push the sink. If you do the opposite, decrease the width, this will make the sink go down. So it looks like if you are pushing or pushing by. In other words, we will say that frequency domain and time domain are the opposite of each other. Yes?
If you had a constant, that creates an impulse function.
If you have if there is only a constant, this will be as an impulse. Correct. Now, with this one, then you can say that there is frequency domain versus time. So we know the relationship like frequency and time as f equal 1 over 2. Right? So omega equal 1 over 2 pi t, this is correct. 2 pi f. Omega equal 2. Omega equal 2 pi times f, or in other words 2 pi over. Okay? Therefore f equal 2 pi over omega over 2 pi or 1 over something like that. So we can say that frequency domain and time domain are the opposite of each other. So if you make the pulse narrower, what will happen to the sink? It will be expanded. if you make the pulse wider, you will make the sink narrower. Okay? So I can say narrower pulse, this leads to wider sink. Or wider pulse, this will make the opposite, which is narrower sink. Okay? Just hear this in mind. If you make it narrower pulse, you will see the high amplitude of the sink. Try to like pushes. But if you make it wider pulse or narrower pulse, then the sink will be expanded. Okay, now let's go to property number 3, which is time shift. When you renew x of TO or T minus TO, x of T minus TO, then the Fourier transform of it, which will be x of omega e power negative j omega T minus. So that shifts will make exponential. This is very similar to Laplace transform. Whenever we have x of t minus t0, this will be x of s e power negative j e power negative st. But here we just substitute this with st omega. The same as Laplace transform. So let me give you this example. Assume that we have x of t like this. Here is the amplitude A. Here is negative t over 2. Here is t over 2. Okay? And it's centered at 0. Then, this is the first one, which is called x of t. Then we have another function, x of t minus t0, which is centered at t0. So this is the pulse amplitude A. Here, t0 minus tau over 2. Here is t0 plus tau over 2. Then how we can make this function? So basically, I can say this is function number 1, this is function number 2. Function number 1, since it's rectangle pulse, it will be as vector function. Or since it's trick, it will be a sinc function. So x of omega will be a tau sinc of omega tau over 2. That's the problem. Now, with number 2, it's the same, but with phase shift TO. So it will be as Fourier transform of x of t minus TO, which will make it x of omega e power negative j omega t naught. So we can substitute x of omega that we know, which is a tau sinc of omega tau over 2 times e power negative j omega t naught. So that's the point. That's it. Just multiply by 80s. Equal negative j omega. Okay? Property number 4. Frequency shifts. Frequency shifts, whenever you have x of omega minus omega naught, which is the opposite of time shift, it will make it x of t e power j omega naught t. So you see here, omega naught, here it will make it omega naught. This is called frequency shift. So you can notice the duality principle, duality, which is between time shift and frequency shift. So let me write here time shift, here is frequency shift. So time shift when you have x of t minus t0, t naught, frequency shift when you have x of omega minus omega naught. This yields to be as x of omega e power negative j omega t naught. This, while the other one is to x of t e power j omega naught. So the things that you can notice in time shifts, it will be negative. frequency shift, it will be positive. Okay? Keep this in mind. Again, you can remember this by don't it. So the tables that we have, they are exactly, or you can, you don't need to memorize this, but keep this in mind. You can go to the formula by looking at the tables. I think the tables, 5 points. Here we use the time scaling, time shift. So you can notice this time shift, this time shift. Now they are the opposites. Okay? Then let's go to property number 5, which is differentiation. Derivative. So in Fourier transform, whenever we have the derivative, dx of t by dt, this will be as j omega x of omega. That's it. There is no initial conditions. Equal Laplace transform. Laplace transform dx of t by dt, it will be s x of s minus x of 0 negative. That was a Laplace transform. But Fourier transform, no initial condition. So we can say Fourier transform no initial conditions. You don't need to worry about x of s. So what you can conclude, the other thing which is in Laplace transform, substitute s equal j omega and no initial condition. This is the Fourier transform. Substitute s as j omega, remove initial condition. This will be as okay. So here are again the similarities between Fourier series and Fourier transform and Laplace transform. Okay, does this make sense? Another thing, how about higher derivative? If you have d of nth derivative x of t by dtn, this will be j omega power n x of omega. Very similar again to Laplace transform, but Laplace transform we used to say s x of 0 bar minus x of 0, etc. So they were used to put initial conditions. But now there is no need for initial conditions. This will make the derivative easier. Now number 6, the property number 6, the integration. How to do the integral. Now we know the integral, or the integral from negative infinity to t, x of tau d tau, it will be as x of omega over j omega plus pi x of 0 delta of omega. Okay, we have a term that was not exist before when we did Laplace transform, but here it is exist. So we have x of 0 like this one, and x of 0 uppercase. So we can say initial conditions are here, but it is not x of 0 like this way, negative. It's not as Laplace transform. It is x uppercase of 0 when omega equals to 0. Okay, how can we find this? We can say that x of 0 can be found by saying it is x of omega, substitute when omega equals to 0. In other words, it will be the integral from negative infinity to infinity, x of t dt, or in other words, area of x of t. So even though there's an initial condition here, but it is not actually initial condition from the time domain. It is the integral, or the area of that function. So mean, if you have x of t something like that, then this this area is x of 0. Okay? Does this make sense? Or in other words, when you have x of omega, substitute omega equal to 0. So let's recall Laplace transform. Laplace transform, the integral from negative infinity to t, x of tau d tau, it was direct x of s over s. So here, no initial conditions. Okay? So the difference is Laplace transform and Fourier transform. Basically, when s equals j omega, the other thing which is include x of 0 times pi delta. Okay? So that's the two differences. So we can say in the integral itself, it's not enough to substitute s as j omega alone. This is not enough. We need to substitute the other term, which is plus pi x of 0 delta omega. Okay? So that's why I say sometimes it's not always to say when we Laplace transform or Fourier transform is just when we substitute s equal j omega in that sense. This is not enough. It's in some situations yes, in some situations it might not be 100% accurate. So that's why we are studying Fourier transform. That's why we will not say, okay, Fourier transform substitutes s equal j omega, then there is no need to study all these properties because it's a special case. The situation actually is not 100% correct because we have some cases that can be different. Any questions? Okay. Let me give an example. If x of omega equal to delta of omega, now I need to find the inverse, which is Fourier transform inverse. What is x of t, which is Fourier inverse of x of omega. There is a general formula, x of t equals 1 over 2 pi, the integral from negative infinity to infinity, x of omega e power j omega t. So you need to be familiar with this form, with this equation, which is the Fourier series inverse. Now keep in mind, if we have numerator, and partial fraction expansion, the others they are still satisfied here. So you need to do the partial fraction expansion. If you have a complex partial fraction, you can do it here. But keep in mind, instead of s, you have j omega squared, etc. So this will still be required. Okay, now with this example, how can we calculate the Fourier series inverse? Fourier transform. Fourier transform. How to calculate the Fourier transform inverse? So we can say x of t equal 1 over 2 pi, the integral from negative infinity to infinity, delta of omega e power j omega t d omega. Now how to find the integral with impulse function, with delta, with the delta function. Do you remember the sampling property of the delta function? Which is integral from negative infinity to infinity delta of t, f of t equal t equals to f of t. Do you remember this? And when we say that from negative infinity to infinity, delta of t minus t0, f of t dt, this means f of t0. Now, we will apply here. Here is f. So it will be f of 0. So we can say from 1 over 2 pi, f of 0, or in other words, substitute t equals 0, 1 over 2 pi, e power j omega t, when t equals 0, and e power 0 will be 1, so it will be 1 over 2 pi. Okay? So as a result, we can say here is time domain, here is frequency or Laplace transform. Not Laplace, Fourier transform. So here, whenever we have 1 over 2 pi, this yields to delta. How about if I have 1? This yields to be 2 pi times delta. Okay? How about if I have a constant c? This yields to be c times 2 pi delta of omega. So if you see any constant, then you multiply by 2 pi times delta of omega. Any constant in time domain will be 2 pi times delta of omega in frequency domain. Okay, does this make sense? While in Laplace transform, delta of t or y, or I think Laplace anyway, you can find it later. Okay, on the other hand, whenever we have from time domain delta of t, what will give you? It will give you 1. Okay? So if you have a constant, it will yield to be 2 pi delta of omega. But if you have delta of t, this yields to 1 for the transform. The plot here is 1. Constant will be equals at 0 to delta t. While the other one, when we have delta of t, delta of t, and when you do the plots, it will be as 1. So when you look at the graphs, you can see, yes, this makes sense, because frequency domain and time domain are the opposite of each other. So you see in this side, look at this side. Look at this side. It was constant 1. Now we need to flip the axis. Flip the axis, it will be delta. Like what we see here, flipping the axis. Then look at delta. It was delta. Then flip the axis, it will be constant. So this is how we can understand it, how this makes sense for us. In time domain, frequency domain. So you will flip the axis from this way to this way. Now let's do some examples. So number 1, which is the Fourier transform of delta of t, and we already did it here, which is 1. Okay? Second one, Fourier transform of u of t. How to find Fourier transform of u of t? I mean, you can go to the table and see it, but we need to prove this. So how do we calculate it? It is Fourier transform of the integral from negative infinity to t. Substitute u of t as the integral from negative infinity to t, delta of tau beta. And since we are dealing with the integral, we can say this is as the integral x of t. So according to the analysis, it will be as x of omega divided by g omega plus pi x of 0 delta omega. Okay? That's the integral property, because this is integral. Because we know u of t is the integral of delta of t, right? Then we know delta of t is 1, then u of t, we can see. So we can say here x of t equal delta of t then x of omega equal to delta equal to 1. So how we can substitute x of omega equal to 1? How to find x of 0? X of 0, substitute omega equal to 0, which will be 1. Because it's 1, substitute omega 0, it will remain 1. Here. X of omega equal to 1, then x of 0 will be 1 as well. Then it will be as 1 over j omega plus pi times 1 times delta omega. Then the final answer will be 1 over j omega plus pi delta omega. So in other words, we can say the Fourier transform of u of t equals to 1 over j omega pi delta omega. Okay? Plus this. We see a term that's different, which is pi plus delta omega. Recall here's time to the Laplace transform, Fourier transform. In time domain, u of t, Laplace transform was 1 over s, Fourier transform 1 over j omega plus pi delta. So we can say Fourier transform substitutes s equal to j omega. This is not enough at all. We have other term. Now the question is, we said sometimes in some situations substitute s equal to j omega, then that's enough. Why in this scenario we need another term? Let's recall last lecture we said that the convergence. We said that s equal j omega, the second thing, convergence on x-axis or on imaginary axis, then it will be true. Substitute s equal j omega. It will be true. S equal to j omega, and enough. That's enough. But in this situation, it's not enough. How? Recall when we wrote the poles. If we say the pole is, for example, the largest, highest pole is located here, then this is convergence here. So if we assume, for example, 1 over s minus 2, something like that, s plus 2, then here s equal to negative 2, then imaginary axis already been included. While the concern is 1 over s, when you plot this, you will see it's located here at the origin. Then the convergence will be here. What does this mean? Imaginary axis is not inside convergence region. That's why saying s equal to j omega alone is not enough. Because imaginary axis is not inside. Okay? While if the imaginary axis is inside the convergence region, then this is true. So again, s equal to j omega enough, can be correct if and only if the imaginary axis is inside the convergence region. Any question? Let's do more example. The sine function. I think you should remember the sine function. It can be sometimes 1, sometimes negative 1. 1 equals 0 is sine. Now we need to find the Fourier transform of the sine function. Okay? So sine function it is u of t or 2u of t minus 1, right? 2u of t minus 1. Then, how to find the sine function, the Fourier transform? Fourier transform of sine function will be 2 Fourier transform of u of t minus Fourier transform of 1. So the Fourier transform of u of t, we can just calculate it as 1 over j omega plus pi delta omega, then minus the Fourier transform of 1, which is 2 pi delta omega. Then to simplify it, it will be as 2 over j omega plus 2 pi delta of omega minus 2 pi delta of omega. This term and this term will cancel each other. This yields 2 over j omega. So in other words, we can say the Fourier transform of sine of t, sine function will be 2 over j omega. Okay? Any question? Now property number 7, which is the frequency derivative. So whenever you have negative j, t, x of t, this yields to be dx of omega over d omega. So there's a duality principle. We call the derivative and frequency derivative. Duality time derivative is frequency derivative. So the time derivative, we said dx of t by dt yields to be j omega, while frequency derivative negative jt x of t, this yields to dx of omega over omega. So keep this in mind. It looks like you swap between these. Swap. So keep this in mind. Now, another example. Find Fourier transform of cosine omega naught t. That's number 1. Number 2, Fourier transform of sine omega naught t. How to deal with this? Let's start with number 1, cosine. As we know, in cosine, we can use the Euler formula, such that cosine omega naught t equal 1/2 e power j omega naught t plus e power negative j omega naught t. Right? That's what we know using the Euler formula. If not, please, if you don't know exactly this, you need to recall Euler formula. And recall, when you do 1 or a constant, it will be 2 pi delta of omega. That was the Fourier transform. Fourier transform is. But when you do e power j omega naught t, this is equivalent to frequency shifts, 2 pi delta of omega minus omega naught. Whenever you have e power negative j omega naught t, this is another frequency shift, 2 pi delta of omega plus delta omega naught. So keep this in mind. Then, since we know this results, we can find Fourier transform. So Fourier transform of cosine omega naught t, applying the linear relationship, will be 1/2 and Euler formula, Fourier transform of e power j omega naught t plus 1/2 Fourier transform of e power negative j omega naught t. Then it will be as 1/2 times 2 pi delta of omega minus omega naught plus 1/2 times 2 pi delta of omega plus omega naught. So as a result, this yields to be as pi delta of omega minus omega naught plus delta of omega plus omega naught. So in summary, it will be as, here is the sine, or is it a cosine? The cosine will be converted from time domain to frequency domain to be like Here is an impulse omega naught, negative omega naught, here is 0, here is pi delta of omega. So omega naught, here is pi delta of omega minus omega naught. So you will use this a lot in communications system course. The last one is just they'll take a few steps, which is to find the sine. Then we will. So number 2, sine omega naught t, which is 1 over 2j e power j omega naught t minus e power negative j omega naught t. Then the Fourier transform of the sine after doing the analysis, you can try it. It will be j pi delta of omega plus omega naught minus delta of omega minus omega naught. That's the answer of the sine as well. So if we need to plot this, here is how is the sine waveform look like in time domain, in frequency domain, or Laplace, not Laplace, Fourier transform. It will look like here is omega naught, here is negative omega naught. At negative omega naught it will be j pi. At omega naught it will be negative j pi. So in other words, I can say sine, cosine, that you will use it a lot in communications, of course. It will be for cosine, impulse, negative omega naught, and sine, it will be, impulse will go down, 1. Okay. Any questions? So I'll see you.